In mathematics, the quaternions are a number system that extends the complex numbers. They were first described by Irish mathematician William Rowan Hamilton in 1843 and applied to mechanics in three-dimensional space. A feature of quaternions is that multiplication of two quaternions is non-commutative. Hamilton defined a quaternion as the quotient of two directed lines in a three-dimensional space, or equivalently as the quotient of two vectors. Quaternions find uses in both theoretical and applied mathematics, in particular for calculations involving three-dimensional rotations such as in three-dimensional computer graphics, computer vision and crystallographic texture analysis. In practical applications, they can be used alongside other methods, such as Euler angles and rotation matrices, or as an alternative to them, depending on the application. In modern mathematical language, quaternions form a four-dimensional associative normed division algebra over the real numbers, and therefore also a domain. In fact, the quaternions were the first non-commutative division algebra to be discovered. The algebra of quaternions is often denoted by H, or in Blackboard bold by. It can also be given by the Clifford algebra classifications C0, 2, CO3, 0. The algebra H holds a special place in analysis since, according to the Frobenius theorem, it is one of only two finite-dimensional division rings containing the real numbers as a proper subring, the other being the complex numbers. These rings are also Euclidean Hurwitz algebras, of which quaternions are the largest associative algebra. The unit quaternions can therefore be thought of as a choice of a group structure on the three-sphere S3 that gives the group spin, which is isomorphic to SU and also to the universal cover of SO. History. Quaternion algebra was introduced by Hamilton in 1843. Important precursors to this work included Euler's four-square identity and Olinda Rodriguez' parameterization of general rotations by four parameters. But neither of these writers treated the four-parameter rotations as an algebra. Carl Friedrich Gauss had also discovered quaternions in 1819, but this work was not published until 1900. Hamilton knew that the complex numbers could be interpreted as points in a plane, and he was looking for a way to do the same for points in three-dimensional space. Points in space can be represented by their coordinates, which are triples of numbers, and for many years he had known how to add and subtract triples of numbers. However, Hamilton had been stuck on the problem of multiplication and division for a long time. He could not figure out how to calculate the quotient of the coordinates of 2 points in space. The great breakthrough in quaternions finally came on Monday, 16 October 1843 in Dublin, when Hamilton was on his way to the Royal Irish Academy, where he was going to preside at a council meeting. As he walked along the towpath of the Royal Canal with his wife, the concepts behind quaternions were taking shape in his mind. When the answer dawned on him, Hamilton could not resist the urge to carve the formula for the quaternions, I2 equals J2 equals K2 equals IJK equals -1, into the stone of Brougham Bridge as he paused on it. On the following day, Hamilton wrote a letter to his friend and fellow mathematician, John T. Graves, describing the train of thought that led to his discovery. This letter was later published in the London, Edinburgh, and Dublin Philosophical Magazine and Journal of Science, Volume XXV, pp. 489–95. In the letter, Hamilton states, "And here there dawned on me the notion that we must admit, in some sense, a fourth dimension of space for the purpose of calculating with triples." An electric circuit seemed to close, and a spark flashed forth. Hamilton called a quadruple with these rules of multiplication a quaternion, and he devoted most of the remainder of his life to studying and teaching them. Hamilton's treatment is more geometric than the modern approach, which emphasizes quaternions' algebraic properties. He founded a school of quaternionists, and he tried to popularize quaternions in several books. The last and longest of his books, Elements of Quaternions, was 800 pages long. It was published shortly after his death. After Hamilton's death, his student Peter Tate continued promoting quaternions. At this time, quaternions were a mandatory examination topic in Dublin. Topics in physics and geometry that would now be described using vectors, such as kinematics in space and Maxwell's equations, were described entirely in terms of quaternions. There was even a professional research association, the Quaternion Society, devoted to the study of quaternions and other hypercomplex number systems. From the mid-1880s, quaternions began to be displaced by vector analysis, which had been developed by Josiah Willard Gibbs, Oliver Heaviside, and Hermann von Helmholtz. Vector analysis described the same phenomena as quaternions, so it borrowed some ideas and terminology liberally from the literature of quaternions. However, vector analysis was conceptually simpler and notationally cleaner, and eventually quaternions were relegated to a minor role in mathematics and physics. A side effect of this transition is that Hamilton's work is difficult to comprehend for many modern readers. Hamilton's original definitions are unfamiliar and his writing style was wordy and difficult to understand. However, quaternions have had a revival since the late 20th century, primarily due to their utility in describing spatial rotations. The representations of rotations by quaternions are more compact and quicker to compute than the representations by matrices. In addition, unlike Euler angles, they are not susceptible to gimbal lock. For this reason, quaternions are used in computer graphics, computer vision, robotics, control theory, signal processing, attitude control, physics, bioinformatics, molecular dynamics, computer simulations, and orbital mechanics. For example, it is common for the attitude control systems of spacecraft to be commanded in terms of quaternions. Quaternions have received another boost from number theory because of their relationships with the quadratic forms. Since 1989, the Department of Mathematics of the National University of Ireland, Maynooth, has organised a pilgrimage, where scientists take a walk from Dunsink Observatory to the Royal Canal Bridge. Hamilton's carving is no longer visible. Historical impact on physics. P.R. Gerard's essay The Quaternion Group and Modern Physics discusses some roles of quaternions in physics. It shows how various physical covariance groups, so the Lorentz group, the general relativity group, the Clifford algebra SU, and the conformal group can be readily related to the Quaternion group in modern algebra. Gerard began by discussing group representations and by representing some space groups of crystallography. He proceeded to kinematics of rigid body motion. Next he used complex quaternions to represent the Lorentz group of special relativity, including the Thomas precession. He cited 5 authors, beginning with Ludwig Silberstein, who used a potential function of one quaternion variable to express Maxwell's equations in a single differential equation. Concerning general relativity, he expressed the Runge-Lenz vector. He mentioned the Clifford biquaternions as an instance of Clifford algebra. Finally, invoking the reciprocal of a biquaternion, Gerard described conformal maps on spacetime. Among the 50 references, Gerard included Alexander Macfarlane and his Bulletin of the Quaternion Society. In 1999 he showed how Einstein's equations of general relativity could be formulated within a Clifford algebra that is directly linked to quaternions. A more personal view of quaternions was written by Joachim Lamberg in 1995. He wrote in his essay If Hamilton Had Prevailed, Quaternions in Physics. My own interest as a graduate student was raised by the inspiring book by Silberstein. He concluded by stating, "I firmly believe that quaternions can supply a shortcut for pure mathematicians who wish to familiarize themselves with certain aspects of theoretical physics." Definition: as a set, the quaternions H are equal to R4, a four-dimensional vector space over the real numbers. H has three operations: addition, scalar multiplication, and quaternion multiplication. The sum of two elements of H is defined to be their sum as elements of R4. Similarly, the product of an element of H by a real number is defined to be the same as the product by a scalar in R4. To define the product of two elements in H requires a choice of basis for R4. The elements of this basis are customarily denoted as 1, I, j, and k. Every element of H can be uniquely written as a linear combination of these basis elements, that is, as A1 plus B plus Cj plus Dk, where A, B, C, and D are real numbers. The basis element 1 will be the identity element of H, meaning that multiplication by 1 does nothing, and for this reason, elements of H are usually written plus B plus Cj plus Dk, suppressing the basis element 1. Given this basis, associative quaternion multiplication is defined by first defining the products of basis elements and then defining all other products using the distributive law. Multiplication of basis elements, the identities, where I, j, and k are basis elements of H, determine all the possible products of I, j, and k. For example, write multiplying both sides of -1 equals I j k by k gives all the other possible products can be determined by similar methods, resulting in which can be expressed as a table whose rows represent the left factor of the product and whose columns represent the right factor, as shown at the top of this article. Non-commutativity of multiplication. Unlike multiplication of real or complex numbers, multiplication of quaternions is not commutative. For example, ij equals k, while g equals -k. The non-commutativity of multiplication has some unexpected consequences. Among them that polynomial equations over the quaternions can have more distinct solutions than the degree of the polynomial. The equation z2 plus 1 equals 0, for instance, has infinitely many quaternion solutions. Z equals B plus Cj plus Dk with B2 plus C2 plus D2 equals 1. So that these solutions lie on the two-dimensional surface of a sphere centered on 0 in the three-dimensional subspace of quaternions with 0 real part. This sphere intersects the complex plane at 2 points I and -I. The fact that quaternion multiplication is not commutative makes the quaternions an often cited example of a strictly skew field. Hamilton product for two elements A1 plus B1I plus C1J plus D1K and A2 plus B2I plus C2J plus D2K. The product, called the Hamilton product, is determined by the products of the basis elements and the distributive law. The distributive law makes it possible to expand the product so that it is a sum of products of basis elements. This gives the following expression. Now the basis elements can be multiplied using the rules given above to get the product of two rotation quaternions will be equivalent to the rotation A1 plus B1I plus C1J plus D1K followed by the rotation A2 plus B2I plus C2J plus D2K. Ordered list form using the basis 1, I, j, k of H makes it possible to write H as a set of quadruples. Then the basis elements are, and the formulas for addition and multiplication are, scalar and vector parts. A number of the former plus 0i plus 0j plus 0k, where A is a real number, is called real, and a number of the form 0 plus B plus Cj plus Dk, where B, C, and D are real numbers, and at least one of B, C or D is non-zero, is called pure imaginary. If a plus B plus Cj plus Dk is any quaternion, then A is called its scalar part and B plus Cj plus Dk is called its vector part. The scalar part of a quaternion is always real, and the vector part is always pure imaginary. Even though every quaternion can be viewed as a vector in a four-dimensional vector space, it is common to define a vector to mean a pure imaginary quaternion. With this convention, a vector is the same as an element of the vector space R3. It is important to note, however, that the vector part of a quaternion is, in truth, an axial vector or pseudovector, not an ordinary or polar vector, as was formerly proven by S.L. Altman in ch. 12 of his 1986 book, Rotations, Quaternions and Double Groups. A polar vector can be represented in calculations by a pure imaginary quaternion, with no loss of information, but the two should not be confused. The axis of a binary rotation quaternion corresponds to the direction of the represented polar vector in such a case. Hamilton called pure imaginary quaternions right quaternions and real numbers scalar quaternions. If a quaternion is divided up into a scalar part and a vector part, i.e., then the formulas for addition and multiplication are, where is the dot product and times is the cross product. Conjugation, the norm, and reciprocal. Conjugation of quaternions is analogous to conjugation of complex numbers and to transposition of elements of Clifford algebras. To define it, let be a quaternion. The conjugate of Q is the quaternion. It is denoted by Q, quart, or conjugation is an involution, meaning that it is its own inverse, so conjugating an element twice returns the original element. The conjugate of a product of two quaternions is the product of the conjugates in the reverse order. That is, if P and Q are quaternions, then equals QP, not PQ. Unlike the situation in the complex plane, the conjugation of a quaternion can be expressed entirely with multiplication and addition. Conjugation can be used to extract the scalar and vector parts of a quaternion. The scalar part of P is 2, and the vector part of P is 2. The square root of the product of a quaternion with its conjugate is called its norm and is denoted Q. In formula, this is expressed as follows. This is always a non-negative real number, and it is the same as the Euclidean norm on H considered as the vector space R4. Multiplying a quaternion by a real number scales its norm by the absolute value of the number. That is, if alpha is real, then this is a special case of the fact that the norm is multiplicative, meaning that for any two quaternions P and Q, multiplicativity is a consequence of the formula for the conjugate of a product. Alternatively, it follows from the identity and hence from the multiplicative property of determinants of square matrices. This norm makes it possible to define the distance d between P and Q as the norm of their difference. This makes H into a metric space. Addition and multiplication are continuous in the metric topology. Indeed, for any scalar, positive I, it holds the continuity follows for vanishing A. Similarly for the multiplication. Unit quaternion. A unit quaternion is a quaternion of norm 1. Dividing a non-zero quaternion Q by its norm produces a unit quaternion UQ called the versor of Q. Every quaternion has a polar decomposition Q equals Q, UQ. Using conjugation and the norm makes it possible to define the reciprocal of a non-zero quaternion. The product of a quaternion with its reciprocal should equal 1, and the considerations above imply that the product of n is 1. So the reciprocal of Q is defined to be this. Makes it possible to divide two quaternions P and Q in two different ways. That is, the quotient can be either PQ-1 or Q-1P. The notation PQ is ambiguous because it does not specify whether Q divides on the left or the right. Algebraic properties. The set H of all quaternions is a vector space over the real numbers with dimension 4. Multiplication of quaternions, for example, is associative in distributes over vector addition, but it is not commutative. Therefore, the quaternions H are a non-commutative associative algebra over the real numbers. Even though H contains copies of the complex numbers, it is not an associative algebra over the complex numbers. Because it is possible to divide quaternions, they form a division algebra. This is a structure similar to a field except for the non-commutativity of multiplication. Finite-dimensional associative division algebras over the real numbers are very rare. The Frobenius theorem states that there are exactly 3 R, C, and H. The norm makes the quaternions into a normed algebra, and normed division algebras over the rails are also very rare. Hurwitz's theorem says that there are only 4 R, C, H, and O. The quaternions are also an example of a composition algebra and of a unit Albanic algebra, because the product of any two basis vectors is plus or minus another basis vector. The set plus or minus 1, plus or minus I, plus or minus j, plus or minus k forms a group under multiplication. This group is called the Quaternion Group and is denoted Q8. The real group ring of Q8 is a ring R, Q8, which is also an 8-dimensional vector space over R. It has one basis vector for each element of Q8. The quaternions are the quotient ring of R, Q8, by the ideal generated by the elements 1 plus, I plus, j plus, and k plus. Here the first term in each of the differences is one of the basis elements 1, I, j, and k, and the second term is one of basis elements minus 1, minus I, minus j, and minus k, not the additive inverses of 1, I, j, and k. Quaternions and the geometry of R3. Because the vector part of a quaternion is a vector in R3, the geometry of R3 is reflected in the algebraic structure of the quaternions. Many operations on vectors can be defined in terms of quaternions, and this makes it possible to apply quaternion techniques wherever spatial vectors arise. For instance, this is true in electrodynamics and 3D computer graphics. For the remainder of this section, I, j, and k will denote both imaginary basis vectors of H and a basis for R3. Notice that replacing I by minus I, j by minus j, and k by minus k sends a vector to its additive inverse. So the additive inverse of a vector is the same as its conjugate as a quaternion. For this reason, conjugation is sometimes called the spatial inverse. Choose two imaginary quaternions P equals B1I plus C1J plus D1K and Q equals B2I plus C2J plus D2K. Their dot product is this is equal to the scalar parts of PQ, QP, PQ, and QP. It also has the formulas the cross product of P and Q relative to the orientation determined by the ordered basis I, j, and k as this is equal to the vector part of the product PQ, as well as the vector part of minus QP. It also has the formula for the commutator PQ equals PQ minus QP. Of two imaginary quaternions one obtains in general, let P and Q be quaternions, and write where PS and QS are the scalar parts, and are the vector parts of P and Q. Then we have the formula. This shows that the non-commutativity of quaternion multiplication comes from the multiplication of pure imaginary quaternions. It also shows that two quaternions commute if and only if their vector parts are collinear. For further elaboration on modeling three-dimensional vectors using quaternions, see quaternions and spatial rotation. A possible visualization was introduced by Andrew J. Hansen.